Hello friends, welcome to Science Talk. This is Jim. I want to discuss with you what's happening in the Sahara Desert. Before I do so, please let me remind you to share my videos, subscribe to my channel, have other people subscribe to my channel, hit the bell so you know when I drop a video. I ask you to please support this work that I do. You can go to patreon.com/Science Talk with Jim Massa, and for a nominal monthly rate of $3 or more, if you're so inclined, you can support the work that I do. So, what's going on with the Sahara? Warming climate increases the spread of the Sahara. In the previous video, I just talked about how the arid west in the U.S. is moving eastward, taking over, it's spreading. We see something similar going on here in the Sahara. Climate change means the Sahara spread is growing, and this spread will displace millions of people. North Africa's pattern of atmospheric change could affect other regions. The spread of the Sahara is now established. It's spreading. The Sahara is growing in size. And this is due to climate change. In the last century, the region of the Sahara, technically defined as desert, has increased by at least 10%. And the area that becomes technically desert, with less than 100 millimeters of rain a year. 10 millimeters to a centimeter, that's 10 centimeters precipitation total per year. 10 centimeters is basically 4 inches. Okay. Has increased in summer, the wet season, over the same period by 16%. So in other words, the area that becomes technically desert has increased in the summer, which is the wet season, by 16%. So if climate change is at work in northern Africa, same may hold true for some of the world's other deserts as well. U.S. meteorologists report in the Journal of Climate that they looked at data from the years 1920 to 2013 to examine annual trends. Deserts are natural geographical features with no fixed boundaries. Parts of them can bloom in rainier years and support crops and even foraging animals, only to become extreme arid zones a year or two later. Okay. Deserts exist because of the natural circulation of the atmosphere. Air rises at the equator, descends in the subtropics, to flow back to the equator near a ground level to establish a pattern of low precipitation. Weather experts call this phenomenon the Hadley Circulation, after the 18th century British natural philosopher George Hadley. Basically, they're vertical convection cells. That's basically what it is. And there are a number of Hadley cells. We have from the equator, subtropic, you go from the subtropic to subpolar, and subpolar to the polar region. So you got a bunch of them that are circulating vertically. Okay. But there's a big one from basically from 0 to 30 degrees north latitude and 0 to 30 degrees south latitude, which is basically the tropics of Cancer and Capricorn, about approximately where those are. Climate change is likely to widen the Hadley Circulation, causing northward advance of the subtropical deserts. This is a statement from Suman Nigam, a professor of atmospheric and oceanic science at the University of Maryland, who is also one of the authors of this study. The southward creep of the Sahara, however, suggests that additional mechanisms are at work as well. So in other words, the expectation is that with the way the Hadley cells flow, is that we can expect to see deserts move northward. They're seeing it move southward. So something else, some other mechanism is at work here. So, what is going on here. The other factors could be that the changing Sahara sand could include a natural climate cycle known to oceanographers and meteorologists as the Atlantic multi-decadal oscillation, sometimes called the North Atlantic Oscillation, the NAO. This is the AMO. Okay. Now, the North Atlantic Oscillation or the Atlantic multi-decadal oscillation could directly be affecting the Sahara situation. There are other such systems. For example, ENSO, El Nino Southern Oscillation, ENSO. That is probably well known to most people and what that does. But there's also the PDO, the Pacific Decadal Oscillation, which tends to tie in with ENSO events. So, how do we separate natural patterns from other trends? Well, that's the headache. And that's what we try, with research, collecting precise data, careful modeling. We try to tease apart. Let's try to separate the natural signal, any variation due to natural signal, from any variation due to other factors such as human impact. I have discussed this before, but it's worth repeating again. When you're developing a model, it could be, I'll use the example of simple linear regression again, just so you get the idea. I could run, I have my data, and I run my regression based on one independent variable. And I get my regression line, and I look at the R-square. The R-square is a value between 0 and 1. 0 means the data ain't worth crap. There's no trend at all. It's like buckshot. 1 means that every single point falls precisely on the regression line. Obviously, that's extremely unlikely. But when you get R-squared values that are, say, like around 0.89, 0.92, that's a pretty good regression model. In fact, that's a very good regression model. Usually we like to see an R-square of about at least 0.85. So now you may have a situation where, okay, I run a regression, I have one independent variable, my R-square is 0.72. Okay. Something might be there, not great. Perhaps when we introduce a second independent variable, we now see that the R-square is 0.97. Ooh. So that means these two independent variables explain 97% of the variation seen in the data. Now that's a good model. In fact, that's an excellent model. Well, we can do that. We can actually, then we can say, all right, we've got these two variables that explain what's going on with my situation here. Now we can then see what proportion does each variable contribute. Okay? Obviously in this case here, 72% was from variable 1, and let's see, 97 minus 7, that's 25 last time I checked. So then 25% of the variation can be explained by the second variable. Okay? We can do the same thing here. We can try to tease out the natural signals, such that we might say, oh, natural variability might account for, say, 26% of the variation. Human activities might account for 60% of the variation. Okay? I think you get the idea of what I'm trying to get at. But that is a task. They have to tease out the natural cycles from any anthropogenic impacts. So, this is what the researchers are now attempting to do to try and tease that very question out. So there's a region called the Chad Basin. And this is region between the shifting dunes of the Sahara and the fertile savannas of tropical Africa lies the Sahel. S-A-H-E-L is how it's spelled. Is it Sahel? Sahel? I'm not sure of the pronunciation. It's a region that goes from Senegal on the Atlantic coast through Mali and Chad to Ethiopia on the Red Sea. Researchers have continuously warned that climate change could bring more famine to this area. Other scientists have said, well, there's more rainfall. So this is where science goes back and forth. You collect the data, you have your debates, and then you see what the data indicates. This is what research is all about. So the Chad Basin falls in a region where the Sahara has crept southward and the lake is drying out. It is a very visible footprint of reduced rainfall, not just locally, but across the whole region. This is a statement from Professor Nigam. The scientists attribute about a third of the shift in the desert's regime to human-induced climate change, the rest to other cyclic weather patterns. Okay, so right now, natural variation seems to be explaining most of the variation. However, there is a approximately 33% variation due to human. Now, there are statistical tests that can be performed to test if such contributions are significant. Researchers have been examining desertification for decades, but this paper is the first, or claimed to be the first, to establish a trend over most of a century, according to Natalie Thomas of the University of Maryland, who led the study. Our priority was to document the long-term trends in rainfall and temperature in the Sahara. Our next step is to look at what is driving these trends for the Sahara and elsewhere, so says Professor Thomas. We have already started looking at seasonal temperature trends over North America, for example. Here, winters are getting warmer, but summers are about the same. In Africa, it's the opposite. Winters are holding steady, summers are getting warmer. So the stresses in Africa are already more severe. So like everything else in science, we need data. You got to collect the data and continually improve the modeling to improve our understanding so that we can get an idea of what is happening. Thank you for your time. Please share this video. Please support my work.